Have you ever tried walking diagonally across a park instead of taking two sides of the path? That single diagonal step is like a resultant vector, a combination of two movements at once. In physics, we often deal with quantities that act simultaneously, like two forces on an object, or wind and boat velocity on a river. To find their net effect, we need to add vectors. But vector addition isn't like adding regular numbers. It requires special techniques because vectors have both magnitude and direction. That's why we use the triangle law and the parallelogram law, graphical methods that respect both size and direction. They help us accurately compute the combined impact of two or more vectors acting on a body. Let's start with the triangle law of vector addition. Imagine two vectors placed end to end, like two steps, one after the other. The triangle law says if two vectors are drawn such that the tail of the second begins at the head of the first, then the third side of the triangle, drawn from the tail of the first to the head of the second, gives the resultant. Let's break it down. First, draw vector A. Then from its head, draw vector B. The resultant vector R is drawn from the tail of A to the head of B. This head-to-tail rule is especially useful when dealing with successive motions, like a car that moves north and then turns east. As shown in the diagram from your textbook, the triangle clearly illustrates how vector addition works visually. Now, let's shift to the parallelogram law, which is used when two vectors originate from the same point and act simultaneously. According to this law, if two vectors are drawn from the same point and completed as adjacent sides of a parallelogram, the diagonal from the origin gives the resultant. So you start by drawing vector A and vector B from the same origin. Then you construct a parallelogram. The diagonal from that common origin gives the resultant vector R. This is perfect for scenarios where multiple forces act on a point object, say the lift force and wind force acting on a flying kite. Here's something cool: order doesn't matter when you add vectors. That's called the commutative law. Whether you go from vector A to B or from B to A, you'll end up at the same resultant vector R. Visually, both triangle and parallelogram constructions confirm this. Next is the associative law. If you're adding 3 or more vectors, it doesn't matter how you group them, the overall resultant remains unchanged. This flexibility helps simplify complex vector chains, like in problems involving multiple displacements or successive forces. As seen in your textbook figures, this property is represented geometrically, confirming that vectors can be grouped or reordered freely during addition. Now let's look at vector subtraction, which might sound tricky but is really just vector addition in disguise. To subtract vector B from vector A, we simply add vector A to the negative of vector B. What's negative B? It's the same magnitude as B but pointing in the opposite direction. So graphically, you draw vector A, then from its head, draw vector negative B. The resultant is from the tail of A to the head of negative B. This technique is essential in solving problems related to relative motion, like to trains moving in opposite directions or a swimmer against the current. Let's work through a powerful example using the triangle law. Problem: two forces act on a point, one is 10 newtons, the other is 8 newtons, and the angle between them is 60 degrees. Find the magnitude of the resultant force. Step 1 represents the vectors as two sides of a triangle with a 60-degree angle between them. Step 2. Use this formula for magnitude of the resultant. R equals square root of A squared plus B squared plus 2 B cosine theta. Now substitute A equals 10, B equals 8, and theta equals 60 degrees. R equals square root of 100 plus 64 plus 2 into 10 into 8 into cosine 60 degrees. That simplifies to square root of 100 plus 64 plus 160 into 0.5, which equals square root of 244, approximately 15.6 newtons. This method blends graphical insight with algebraic precision, and it works beautifully. Let's quickly recap what we've learned today. To combine vectors, whether forces, velocities, or displacements, we use graphical methods like the triangle and parallelogram laws. These methods consider both magnitude and direction, giving us an accurate resultant. We learned that vectors follow the commutative and associative laws, so the order and grouping of addition doesn't affect the outcome. For subtraction, we simply add the negative vector, helping us solve problems in opposing directions. Mastering these visual techniques lays the foundation for analytical methods you'll use next, especially in projectile motion, circular dynamics, and relative velocity. I hope this session gave you a clear picture of how vectors combine and behave in real-world physics. See you in the next topic, where we learn how to resolve a vector into components.